In 1933, Fritz Zwicky claimed a dying star could shrink to a city-sized neutron ball. His peers at the American Physical Society laughed at his 10-kilometer-wide stellar corpse prediction. But you right now contain neutrons from ancient supernovae, forged in exactly such collapses. Zwicky, who coined supernova in English, often chain-smoked cigars while making this breakthrough. To grasp his radical vision, we must first understand the life cycle of stars themselves. A star like our Sun burns hydrogen for billions of years, but massive stars, those between 8 and 20 times the Sun's mass, end their lives in catastrophic collapse. The question Zwicky posed was deceptively simple. What happens when gravity wins? For most of a star's life, it maintains a delicate balance. The outward pressure from nuclear fusion pushes against the inward crush of gravity. But when a massive star exhausts its nuclear fuel, fusing hydrogen into helium, then helium into carbon, and so on, until it reaches iron, the fusion stops. Iron cannot fuse without consuming energy, and with no outward pressure, the star's core has nothing left to hold itself up. Gravity takes over completely. The core collapses inward, at speeds reaching 25% of the speed of light. In less than a second, a ball of iron the size of Earth is compressed to the density of an atomic nucleus. Protons and electrons are literally forced together, transforming into neutrons. The entire mass of the star's core, more than the mass of our Sun, is squeezed into a sphere just 20 kilometers across, smaller than Manhattan, smaller than Paris, smaller than most cities you have ever walked through. The outer layers of the star, now unsupported, crash inward and then rebound off this impossibly dense core, producing the supernova explosion that can briefly outshine an entire galaxy. Zwicky and his colleague Walter Baade proposed their neutron star theory at a conference in December 1933, and published their seminal paper in 1934, but the idea was so radical that most physicists dismissed it as speculation. How could matter exist at such densities? A single teaspoon of neutron star material would weigh 10 million tons. The atoms themselves would be crushed out of existence, leaving only a sea of neutrons held together by gravity and a quantum mechanical force called neutron. Degeneracy pressure, the same principle that prevents white dwarfs from collapsing, but at a far more extreme scale. Consider this. Our Sun has been burning for 4.5 billion years and will continue for another 5 billion. Over its entire 10 billion-year lifetime, the total energy output of the Sun is colossal beyond comprehension. Now imagine that same amount of energy released not over billions of years, but in a matter of seconds. That is what Baade and Zwicky calculated a supernova produces. The numbers were so extreme that most astronomers simply refused to believe them. What physical process could possibly account for such a release? Nuclear fusion, the engine that powers stars, could not explain it. The energy output was orders of magnitude too high. Zwicky and Baade made a leap that was as brilliant as it was audacious. They proposed that the energy of a supernova did not come from nuclear reactions at all. It came from gravity, specifically from the gravitational collapse of an ordinary star into an object of unimaginable density, what they called a neutron star. The idea was simple in concept, but radical in implication. When a massive star exhausts its nuclear fuel, its core can no longer support itself against gravity. It collapses catastrophically, and the gravitational potential energy released in that collapse is converted into the blinding fury of the supernova explosion. What remains is the collapsed core itself, a ball of matter so dense that protons and electrons are literally crushed together, merging into a sea of neutrons. The scientific community did not embrace this idea. They mocked it. Neutron stars had never been observed. They existed only in the mathematics of general relativity and in the fevered imagination of a Swiss astronomer who was notorious for his abrasive personality. Zwicky was known to call his colleagues spherical bastards because, he explained, They were bastards from every direction you looked at them. He was brilliant, but he was also combative, dismissive, and utterly convinced of his own correctness. That combination does not win friends in academia. Most physicists dismissed the neutron star as a theoretical fantasy. Matter at nuclear density, a teaspoon weighing 10 million tons, was considered physically impossible by the standards of the time. How could atoms themselves survive such compression? The answer, of course, was that they could not. The atoms would be destroyed, leaving only a degenerate gas of neutrons held together by gravity and the Pauli exclusion principle. 6 years later, in 1939, another physicist took up the problem. J. Robert Oppenheimer, working with his student George Volkoff at the University of California, Berkeley, calculated the theoretical maximum mass that a neutron star could sustain before gravity overwhelmed even neutron degeneracy pressure. Their paper established the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 times the mass of our Sun. Above that limit, not even neutrons could resist the crush. The object would continue collapsing into something else entirely, something from which no light could escape. But in 1939, no one had ever seen a neutron star. They were purely theoretical objects, mathematical curiosities on paper. Oppenheimer himself would soon abandon astrophysics for a far more urgent project in Los Alamos, and the neutron star would remain a ghost in the equations for nearly 3 decades. The prediction was made, the limit was calculated. Now all that remained was to find one. The irony of this publication is almost unbearable. In September 1939, the same month the paper appeared in print, Germany invaded Poland. World War II had begun. Oppenheimer, a Jew deeply aware of the rising fascist threat, was already being recruited for a secret project that would consume the rest of his career. Within 3 years, he would be directing the Los Alamos laboratory, building a weapon that derived its power from a different kind of nuclear physics, fission, not collapse. The man who calculated the upper limit of neutron star stability would soon help create the most destructive force humanity had ever unleashed. And so the Tov limit, this profound prediction about the fate of massive stars, was published and then largely forgotten. The world had other concerns. Europe was burning. Physicists were fleeing to America. The Manhattan Project consumed the best minds of a generation. Neutron stars remained theoretical ghosts, objects that existed only in the equations of a 1939 paper that few people read and fewer believed. For nearly 3 decades, the Tov limit sat in the scientific literature like a time capsule, waiting for someone to open it. The year was 1967, and the place was the University of Cambridge. A 24-year-old graduate student from Northern Ireland named Jocelyn Bell Burnell was spending her days and nights analyzing miles of chart paper from a radio telescope she had helped build, a sprawling array of 2,000 dipole antennas spread across 4.5 acres of English countryside. The telescope was designed to study quasars, those distant, enigmatic objects that were then the frontier of astrophysics. But the universe had other plans. Bell Burnell noticed something strange in the data. A signal, not the random hiss of cosmic background radiation or the steady hum of human interference, but something regular, too regular. A pulse, every 1.337 seconds, like a metronome in the sky. The timing was so precise, so consistent, that it defied any known natural explanation. She brought the anomaly to her advisor, Anthony Hewish, a radio astronomer who had designed the telescope. Neither of them could explain it. The signal was narrowband, meaning it was confined to a specific radio frequency, and it appeared at the same sidereal time each day, meaning it was coming from a fixed point in the sky, not from Earth. The team began to joke nervously that they might have found something extraordinary. They labeled the source LGM1 Little Green Men. It was half a joke, but the half that was serious kept them awake at night. Could this be the first evidence of extraterrestrial intelligence? A beacon broadcasting from somewhere in the constellation Vulpecula. The implications were staggering. Burnell spent weeks methodically ruling out every possible source of interference, passing aircraft, satellites, radio transmitters, even faulty wiring in the telescope itself. She was staring at the first pulsar in history, and she didn't know what she was looking at. The breakthrough came when she discovered a second source, pulsing at a different frequency in a different part of the sky. Two signals, both impossibly regular, both coming from different directions. The probability of two separate extraterrestrial civilizations broadcasting on the same frequency at the same time was vanishingly small. The little green men hypothesis collapsed. What remained was something far stranger, far more beautiful, and far more profound. Burnell and Hewish realized that the only physical object capable of producing such regular pulses was a rapidly rotating star with an intense magnetic field, a star that had been crushed to the density of an atomic nucleus, emitting beams of radiation from its magnetic poles like a lighthouse. As the star spun, the beams swept across Earth once per rotation, producing the regular pulse. The object was a neutron star. Zwicky and Baade's 1933 prediction, Oppenheimer and Volkoff's 1939 mass limit, all of it had been waiting in the mathematics for 34 years, and now a graduate student with a roll of chart paper had found the proof. The discovery was published in Nature in February 1968, under the title Observation of a Rapidly Pulsating Radio Source. The paper was authored by Hewish, Burnell, and 3 other members of the team. The scientific world was electrified. Within months, other observatories confirmed the finding and discovered more pulsars. The name stuck, short for pulsating radio source. Neutron stars were real. The TOV limit was real. The most extreme objects in the universe, predicted by theorists who had been mocked and ignored, were suddenly the hottest topic in astrophysics. But the story did not end there. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish and to Martin Ryle, another radio astronomer, for the discovery of pulsars. Jocelyn Burnell, the person who actually detected the signal, who spent months analyzing the data, who refused to dismiss the anomaly as noise, was not included. The omission sparked immediate controversy. Hewish himself acknowledged Burnell's role, but the Nobel Committee's decision stood. It remains one of the most debated moments in the history of the prize, a case study in how the contributions of early career scientists, particularly women, have been overlooked by an institution that rewards seniority. Burnell handled the snub with extraordinary grace. She continued her career in astronomy, making significant contributions to the study of pulsars and X-ray astronomy. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million. She donated the entire amount to fund scholarships for women, underrepresented minorities, and refugee students in physics. When asked about the Nobel controversy decades later, she said simply, "It doesn't matter. The discovery was what mattered." But it does matter. It matters because the story of the neutron star is not just a story of gravity and quantum mechanics. It is a story of who gets credit, whose work is seen, and whose name is written into the history books. Today we have the tools to study these objects directly. The first pulsar was found in 1967, and within a decade hundreds more were catalogued. We now know that neutron stars are not just theoretical curiosities. They are among the most extreme objects in the observable universe. They measure roughly 20 kilometers across, yet pack more mass than our Sun. They spin at rates that defy intuition. The fastest known pulsar, designated 7482446 AD, rotates 706 times per second. Its surface moves at nearly a quarter of the speed of light, and their magnetic fields are beyond comprehension. 1 trillion times stronger than Earth's, capable of distorting the very structure of atoms. But the Tolman-Oppenheimer-Volkoff limit, that theoretical boundary between neutron star and black hole, remains an open wound in physics. In 1939, Oppenheimer and Volkoff calculated the limit at roughly 0.7 solar masses, But that was based on an idealized model of a cold, non-interacting neutron. It has. Real neutron stars are far messier. Their interiors contain not just neutrons, but a soup of exotic particles, hyperons, mesons, perhaps even deconfined quarks. The exact value of the Tove limit depends on the unknown equation of state of nuclear matter, at densities far beyond anything we can create in laboratories. Current estimates, based on observations of neutron star mergers and the most massive pulsars ever detected, place the limit between 2.0 and 2.3 solar masses. But the uncertainty is still significant. We do not know exactly where the threshold lies. That uncertainty was thrust into sharp focus on August 17, 2017, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the merger of two neutron stars. The event, designated GW 70817, was a watershed moment in astronomy. For the first time, we observed the same cosmic catastrophe through two completely different messengers, gravitational waves and electromagnetic radiation. Telescopes around the world and in space turned toward the source, a galaxy called NXC 4993, located 130 million light-years away. What they saw confirmed a decades-old theory. The collision of neutron stars is the forge where heavy elements are created. The gold in your wedding ring, the platinum in your electronics, the uranium in nuclear reactors. Much of it was born in the violent merger of two city-sized stars scattered across the universe by the explosion. This is the legacy of Zwicky, Baade, Oppenheimer, and Volkoff. They opened a door to a universe far stranger than anyone imagined. A universe where stars can be crushed to the size of cities, where a single teaspoon of matter weighs 10 million tons, where time itself slows down near the surface of these objects due to extreme gravitational time dilation. A neutron star is a cosmic monument to the power of gravity, and a reminder of how much we still do not understand. The universe compresses suns into cities. It turns the impossible into the observed. And it reminds us that the strangest theories are often the ones that turn out to be true. Zwicky was mocked for proposing neutron stars. Oppenheimer calculated their limit and then walked away to build a bomb. Burnell found the first one and was denied a Nobel Prize. Yet here we are, nearly a century later, still trying to answer the questions they left behind. The universe is not only stranger than we suppose, it is stranger than we can suppose.